Welcome to the next part of chemistry chapter, metals and non-metals. So in this part we are going to discuss about the first uh, part of this lecture would be about how do metals and non-metals react, which is a easy topic, not very lengthy and comparatively simple. Not much to memorize over here, but to understand a few things. After which we are going to understand about metallurgy, that is extraction of metals. So let's try to finish as much as we can in this part, in this today's lecture. Let's begin. So as we already have learned, metals have 1 to 3 electrons in their outermost shells. Please take notes, keep your pens and notebooks with you. Whatever important points you find, please note them down. So for you, it is easier to form answers when you are when I give you homework or when you are writing some test. You can easily form answers because you have taken down the notes and your concepts are clear. So metals have 1 to 3 electrons in their outermost shells and non-metals have 4 to 8 electrons. Now some places they write 4 to 7 electrons because the elements which are having 8 electrons in their outermost shell are generally not considered as non-metals, nor they are considered as metals. They are noble gases, right? So it is accurate to say that non-metals have 4 to 7 electrons and metals have 1 to 3 electrons in their outermost shell. So what are these electrons known as? These are valence electrons, and valence electrons are responsible for the chemical reactivity of any element. So what about the atoms which contain 8 electrons in their outermost shell? Their outermost shell is said to be completely filled and they are known as noble gases, except helium, which is also a noble gas, but its outermost shell has only 2 electrons because it has just one shell. Still, it is a noble gas and its outermost shell or the first shell is completely filled, so it does not react. Okay, now if you see this table carefully for your reference, uh, there are electronic configurations of all the elements from atomic number 1 to 20. There is no hydrogen over here, but yeah, mostly all of the elements are here, and also I can't see lithium, but it's okay. Mostly all of the elements present in the periodic table from atomic number 1 to 20 are over here. And as you can see, metals, they generally have 1, 2 or 3 electrons in their outermost shell. Non-metals have 5, 6, 7. 4, the non-metal with 4 electron in the outermost shell, for example, carbon is not shown over here, but it's okay. We are mostly concerned with metals which has 1, 2 or 3 electrons in their outermost shell and non-metals which have 5, 6 or 7 electrons in their outermost shell. And the noble gases have 2 or 8 electrons in their outermost shell. That is 2 in the case of helium only because it has just one shell. Okay, so these are some electronic configurations of some elements. I'm sure you know what is an electronic configuration. You have studied that in class 9th, right? That is the distribution of electrons in the shells. So noble gases are generally very stable and show very little reactivity. Actually, they do not show any reactivity, but in some cases, they exhibit some characteristic properties, and that's why they have written little reactivity. It is clear from the table that except for helium, All other noble gases have 8 electrons, which is known as octet in their outermost shell. Helium, on the other hand, has only 2 electrons in its first shell, outermost shell, that is known as duplet. Because the first shell cannot have more than 2 electrons. This means that noble gases have completely filled outermost shell. Since noble gases do not take part in bonding, this means that 8 electrons in the outermost shell represent 8 electrons in the outermost shell represent a highly stable electronic configuration. So if the outermost shell has 8 electrons, octet, it is a highly stable electronic configuration. Also, a duplet is highly stable electronic configuration in case of helium only. So due to this stable electronic configuration, the noble gases have neither any tendency to lose or gain electron. They don't have any tendency to lose or gain electron. So they remain as such and exist as monatomic. They remain as such means they are unreactive. They do not react, they do not donate or accept electrons, and they remain monoatomic. Actually, this word monoatomic, if you see the actual spelling of this word, this is not the correct spelling, but yeah, it can be spelled in more than one ways. The actual spelling of this word is monatomic. Monatomic means mon comes from the word mono, means one. Atomic means there is one atom in each molecule of a noble gas. That is, noble gas do not exist as molecules. They exist independently as atoms. Noble gases are such elements in the periodic table which exist as as independent atoms in the universe, you can say. Okay, so noble gases, they have stable electronic configuration, then they occur as independent atoms around us because of their tendency to remain stable, to remain, you can say, unreactive, since they don't have any requirement of accepting or donating electrons. What about sodium? Sodium is a metal, and sodium has one electron in its outermost shell. So sodium, which has electronic configuration of 281, wants to achieve an electronic configuration to its nearest noble gas. Now if you see the nearest noble gas to sodium, the nearest noble gas to sodium is neon, because you see the atomic number of sodium is 11 and the atomic number of neon is 10. So sodium wants to achieve an electronic configuration just like neon. Sodium wants to achieve an electronic configuration just like neon. So from 281 it wants to become 28. It wants to become 2,8. So that means sodium will have a tendency, in order to become from 281 to 28, in order to change its electronic configuration to its nearest noble gas, it would want to donate one electron. So sodium, what it does is, do you see this dot on sodium? This dot represents that one single electron in its outermost shell. So what is the tendency of sodium? Sodium tends to lose one electron in its outermost shell. So when it loses this one electron, its electronic configuration now becomes like neon 2,8. It becomes chemically stable. But guess what? Initially, sodium had how many electrons? 11. And how many protons? 11. So it was electrically neutral. Yes, it was chemically unstable, chemically reactive. Sodium was chemically reactive, but it was electrically neutral. What about sodium ion? Sodium ion has how many electrons? 10 electrons. What about the protons? Protons are not lost. Protons are as it is in the nucleus. So it has how many protons? 11. 10 electrons, 11 protons. Now it is positively charged. It is no more electrically neutral. It has acquired, it has acquired a positive charge, unit positive charge. You see this plus sign that shows one positive charge. But it is chemically stable, just like neon. Electrically charged but chemically stable. That's what happens to sodium when it loses one electron. Okay, now since it has less electrons than the number of protons, you see this plus sign over here. Plus sign means it has unit positive charge. Yeah, if it would have lost, if some atom X would have lost 2 electrons, then we would write 2 plus. How many electrons an atom loses or gains, that number is shown in the superscript. And if it gains electron, then you put minus sign. If it loses electron, you put plus sign. 2 plus. 2 plus is not plus 2. It is not an integer. Okay. 2 plus is simply showing you the number of electrons one atom donates or loses. Okay. So this is what happens to sodium, and not only sodium. What about magnesium? Magnesium has 2 electrons in the outermost shell. Now magnesium would also like to become like neon, right? So magnesium would lose 2 electrons. So magnesium would become Mg2 plus after losing 2 electrons. What about aluminium? It has 3 electrons in its outermost shell. Who would it want to become like? Again, neon. Aluminium would also like to become like neon. So aluminium will lose 3 electrons and become Al3 plus. It acquires 3 positive charge. 3 units of positive charge. Yes, you can say like that. 3 plus. So these numbers which you see in the superscript above the symbol of any element, that number shows its valency. And what is valency? Valency is the number of electrons accepted or donated by an atom in order to complete its outermost shell. You have studied everything about this, whatever I am talking in class 9. This is just a revision for you so that you know how metals and non-metals react. This is not our topic. Let's talk about chlorine, which is basically a non-metal. So chlorine atom is exhibited like this, shown like this. Do you see? There is a symbol chlorine, Cl, capital C, small l, and there are 7 dots around it. So what are these 7 dots? If you see, its electronic configuration is 2, 8, 7. So the 7 electrons present in the outermost shell of chlorine are shown by dots over here. Okay. Now its electronic configuration is 2, 8, 7. It is chlorine, a non-metal. To complete its outermost shell, let me show you. Let me show you the chart of electronic configuration of various elements. Here, chlorine is right here. Atomic number 17, electronic configuration 287, number of valence electrons or the number of electrons in outermost shell 7. Now, chlorine wants to achieve a stable electronic configuration which is just like its nearest noble gas. So I would like you to see or observe the nearest noble gases, or you can say all the noble gases. I would want you to observe and find out which noble gas is the nearest one to chlorine. Now to find that out, I would want you to look or focus at the atomic number. What is the atomic number of chlorine? 17. See, atomic number is equal to the number of protons, which is equal to the number of electrons present in any atom of any element. Okay, you know this, you have studied in class 9th. Now, atomic number of the noble gases are over here. Which is the atomic number which is closest to 17? 2, 10, 18 or 36? Which atomic number is closest to 17? Of course 18. So the nearest noble gas of chlorine is argon. The nearest noble gas of chlorine is argon. So chlorine would want to achieve an electronic configuration just like argon. So chlorine, from having electronic configuration 287, it would want to have an electronic configuration like 288. Why the nearest noble gas? Some people might have this question. Because it is easy like that for them. It is easier for them that way. For any element to achieve the electronic configuration of their nearest noble gas and to achieve stability that way, it's easier, it is natural. So for chlorine to become like argon, it is very natural. But how would it become like argon? See, argon has 8 electrons in its outermost shell. Chlorine has 7. Apart from that, there is no difference in the electronic configuration. So to achieve 8 electrons, what does chlorine do? To achieve 8 electrons, chlorine would want to gain 1 electron in its outermost shell. Did you notice about the metals? What do metals try to do? What is their tendency? Their tendency is to lose electrons. Since they have 1, 2 or 3 electrons, it is easier for metals to lose electrons and achieve stable electronic configuration. But what is easier for non-metals? Since non-metals have 5, 6 or 7 electrons in their outermost shell, they tend to lose electron. They tend to gain electron. Their tendency is to gain electron. So chlorine would also want to gain electron and become or achieve a stable electronic configuration just like its nearest noble gas, argon, that is 288. So here you can see chlorine is accepting 1 electron, gaining 1 electron and becomes chloride ion, which has a unit negative charge. Now, as similar to sodium, we will analyze what happens with chlorine over here. So chlorine initially had 17 electrons and 17 protons. It was chemically reactive but electrically neutral. Chemically reactive but electrically neutral. What about chloride ion? See, chloride ion, Cl minus, it has 18 electrons but 17 protons. How come it has 18 electrons? Because it gains 1 electron. So it becomes chemically stable. It becomes chemically stable, but electrically charged. That is, it acquires a negative charge. How much negative charge? Single unit negative charge. Right? So chlorine acquires a unit negative charge on gaining one electron, and its symbol becomes Cl1 minus or just Cl minus. Compare it with sodium. Sodium acquired a unit positive charge, and it was written as Na1 plus or Na plus. Chlorine is written as Cl1 minus or Cl minus. That is the difference. Now, do you understand the whole scenario? Now, in this whole process, if you look at these two reactions together, not separately, but together as in, suppose if you are studying about how sodium and chlorine both achieve stability. Sodium has a tendency to lose one electron, chlorine has a tendency to gain one electron. So sodium and chlorine decides to undergo this mutual exchange of electrons. That is, sodium will give its electron to chlorine, chlorine will take one electron from sodium, and that way both the atoms' needs will be fulfilled. Both will achieve chemical stability. So just imagine sodium is giving one electron to chlorine, chlorine is taking that one electron from sodium. In this process, so just imagine sodium has acquired a positive charge by losing one electron. Chlorine has acquired a negative charge by gaining one electron. Both have acquired a stable electronic configuration, but since both are oppositely charged, they are held together by strong electrostatic forces or electrovalent or ionic bond. So this is how metals and nonmetals react with each other. By respective losing and gaining electrons, they acquire equal and opposite charges, and they are held together by the electrostatic forces of attraction, which is known as electrovalent or ionic bond. Okay, so here the electrons are shown by dot and cross. These representation of atoms with their valence electrons as dots and crosses are known as Lewis dot structure or electron dot structure. Okay, so with the help of electron dot structure, we can simply show that which atom is losing electron, which atom is gaining electron, and how their electronic configurations are becoming complete or stable, and how they are acquiring charges, and how they are held together by electrostatic forces. So the compound formed is called ionic compound or electrovalent compound. Thus we can say that all atoms other than noble gases have less than 8 electrons in their outermost shell. Absolutely correct. Therefore they combine with each other or with other atoms to get stable electronic arrangement of noble gases. So the tendency of atoms of various elements to get stable electronic configuration of 8 electrons in their valence shell is the cause of formation of chemical bond. This principle of attaining maximum 8 electrons is also called octet rule. Okay, so atoms generally have atoms of metallic and non-metallic elements have tendency to attain stable electronic configuration, and this tendency of attaining stable electronic configuration results in the formation of bonds. Okay, so a chemical bond is formed by, I don't know, bond is bond formed between, acquire the stable noble gas configuration is called. Okay, so some part is missing. Let me finish it. Let me complete this part. A chemical bond formed between two atoms by mutual exchange of electrons to acquire the stable noble gas electronic configuration is called ionic bond or electrovalent bond. Okay, so some part is missing which I just completed. A chemical bond formed between two atoms by mutual exchange of electrons to acquire the stable noble gas configuration is called ionic or electrovalent bond. The number of electrons lost or gained by the atom is called its electrovalency. The number of electrons lost or gained by the atom is called its electrovalency, and the compound thus formed are called ionic compounds or electrovalent compounds. Okay, for example, in sodium chloride, the electrovalency of sodium is 1 plus, and that of chlorine is also 1 but 1 minus. Let us consider the formation of some more ionic compounds like magnesium chloride. So magnesium has got 2 electrons in its outermost shell. Its electronic configuration is 282. Chlorine's electronic configuration is 287. So what is happening with magnesium chloride? Let us look at the formation of magnesium chloride separately. So since magnesium has got 2 electrons in its outermost shell, I'm showing electrons with the help of dots, and one chlorine has got 7 electrons in its outermost shell. What magnesium will do is donate its electron to chlorine, but magnesium will have one more electron in its outermost shell which it wants to donate to somebody. So this chlorine, which has got just one space in its outermost shell, will summon one more chlorine. So one more chlorine will be ready to accept one electron in its outermost shell. So this one electron goes to another chlorine atom. So magnesium donates both of its valence electron to one of the chlorine, two chlorine atoms, one electron each. And this results into the formation of magnesium chloride, in which the magnesium has acquired 2 plus charge, which is basically attracted by chlorine, which acquires 1 minus unit negative charge, chlorine 1 minus unit negative charge. So this is how magnesium chloride, that is MgCl twice magnesium chloride compound or molecule is formed. So this magnesium chloride, since it is formed by mutual exchange of electrons between the atoms of metal magnesium and non-metal chlorine, that's why it is known as electrovalent or ionic compound. Okay, you see these lines here between the atoms or ions of magnesium and chlorine. These are uh, let me tell you, these are electrostatic force of attraction. So between the respective ions of opposite charge, there are electrostatic forces of attraction, which from which this name has been given to this particular bond, that is electrovalent or ionic bond. And this compound is known as electrovalent or ionic compound. Okay, so Yes, there is one more example, formation of magnesium oxide. Now, how is magnesium oxide formed? Let's see over here. Magnesium, which has got, uh, let me, okay, magnesium, which has got 2 electrons in its outermost shell, and oxygen, which has got 6 electrons in its outermost shell. Oxygen requires 2 electrons to complete its outermost shell, and magnesium needs to donate 2 electrons. So magnesium decides to donate its 2 electrons to oxygen. And in this process, what happens is magnesium acquires 2 plus charge and oxygen acquires 2 minus charge. Always remember the atom which loses electron acquires a positive charge. If it loses 2 electrons, it acquires 2 unit positive charge. An atom which gains electron acquires negative charge. If it gains 2 electrons, then it acquires 2 unit negative charge. And this is how magnesium oxide is formed. Its chemical formula is MgO. It's an electrovalent or ionic compound. Very simple. So this is known as Lewis dot structure or electron dot structure. Lewis dot structure or electron dot structure. Okay, so you should be able to represent the compound formation of compounds in this manner. Okay, so here some structures of some common ionic compounds are given to you. I would recommend that you form or you show these structures in your notebook as notes. Sodium chloride, magnesium fluoride, calcium oxide. Now here for magnesium fluoride they have shown 2F. Okay, but my method of showing magnesium chloride, if you see, I had shown 2 chlorines separately. So if you do with my method, it'll be better actually. So because it has more clarity. But yeah, all these compounds which you see, you have to form their electron dot structures and show that how these compounds are formed, how these electrovalent or ionic compounds are actually formed. Okay, so the important characteristic properties of ionic compound. Let's look at these. Ionic compounds consist of ions. Ionic compounds consist of ions. All ionic compounds consist of positively and negatively charged ions and not molecules. Remember that. This is the most important part. Ionic compounds do not have molecules. They have ions. For example, sodium chloride consists of Na plus and Cl minus ions. Magnesium fluoride consists of Mg2 plus and F minus ions and so on. Ionic compounds are solids. In general, in ionic compounds, the ions are held together by strong electrostatic forces of attraction. Hence, ionic compounds are solids and relatively hard, in which the ions have regular close packed structure. So the structure of ionic compound is close packed structure, and hence we can say that ionic compounds are solids and hard. These compounds are generally brittle and break into pieces when subjected to pressure or stress. They are also generally brittle. The ionic compounds in general are crystalline in nature. What do you mean by crystalline? Crystalline means their shape is crystalline, just like crystals. So X-ray studies have shown that ionic compounds do not exist as simple single molecule as NaCl. This is due to the fact that forces of attraction are not restricted to a single unit such as Na plus or Cl minus, but due to uniform electric field around an ion. Remember this, due to uniform electric field. Electric field is the space in which this electric forces of attraction or repulsion are visible. So due to the electric field around an ion, each ion is attracted to a large number of other ions. For example, one Na plus ion will not attract only one Cl minus ion, but it can attract as many negative charges as it can. Similarly, the chloride ion will attract several sodium ions. As a result, there is a regular arrangement of these ions in three-dimensional shapes as shown in figure. Such regular arrangement is called a lattice. So they have given you the meaning of lattice over here. So all electrovalent compounds are in the form of lattice. They exist in the form of lattice. Do you see this? It's just like a cuboidal structure where dark red color dot is sodium ion and hollow red color dot is chloride ion. So they are arranged in the form of lattice. They form this three-dimensional cuboidal structure which is known as a lattice. This is because the mutual attraction between any positive or negative ion with multiple ions of oppositely charged nature. Okay, so this is how ionic compounds occur, and that's why they are crystalline in nature. As it can be seen from the figure, the oppositely charged ions are arranged in a regular manner. It has been seen that the arrangement of sodium chloride lattice is such that each sodium ion is surrounded by 6 chloride ions and each chloride ion is surrounded by 6 sodium ions as shown in the figure. So as you can see here, each sodium ion is surrounded by 6 chloride ions, two on the left and right, two on the top and bottom, and two on the in the front and back. And each chloride ion is also surrounded by 6 sodium ions, two on the left and right, two on the top and bottom, and two on the front and back, right? So if you see this structure this way, you can figure out that how these ions are, above each other and around each other. This compound has equal number of opposite charged ions, so it will have no charge. But what is its formula? NaCl, or Na plus 100 and Cl minus 100, or Na plus NCl minus N. In fact, sodium chloride has an extended lattice in 3 dimensions. Okay, so see, in one crystal of sodium chloride, there are, you can say, millions of sodium and millions of chloride ions. So we can't say that its formula is, let's say, Na. NaCl is its just symbolic formula. Okay, NaCl. This shows that one molecule has got one sodium ion and one chloride ion, but that's just you can say hypothetical, because sodium chloride does not have molecules. It has a lattice like this, a structure which has multiple sodiums and chloride ions. So actually it should be written as NaNClN, its molecular formula, and here N is maybe millions of sodium or chloride ions which are arranged in this kind of lattice. But for simplification, we use NaCl. Okay. Now the whole structure must be clear in your mind. Let's go ahead. Ionic compounds have high melting and boiling points. So the ionic compounds have high melting and boiling points. This is because the strong electrostatic forces of attraction between the oppositely charged ions. Therefore, large amount of energy is needed to break these bonds, and hence melting and boiling points are very high and their densities are also very high. So the melting and boiling points of some common ionic compounds are given here. This is lithium chloride, sodium chloride, potassium bromide, potassium iodide, calcium oxide, magnesium chloride, calcium chloride. You see high melting and boiling points. compared with covalent bond between two nonmetals. Ionic compounds are generally soluble in water and other polar solvents. So you must be having this doubt about what is polar solvent. Polar solvents are solvents of covalent compounds. For example, polar solvents like water. Water is a very common polar solvent. So what water does is water breaks the uh, intermolecular forces of attraction which uh, exist between the ions of ionic compounds. So water and other polar solvents, they break these forces of attraction and can easily dissolve ionic compounds. But ionic compounds, since they are water soluble in water, they are insoluble in non-polar solvents like benzene, ether, alcohol, carbon disulfide, and so on, acetone. So these are non-polar solvents. Non-polar solvents are organic solvents. Okay? So in organic solvents, ionic compounds are insoluble. But in inorganic solvents like water, polar solvents like water, ionic compounds are soluble. Ionic compounds conduct electricity when dissolved in water or melted. They do not conduct electricity in solid state, because in solid state the ions are, they are closely, you can say, tightly packed with each other and attracted by each other. Okay, they have very rigid structures in solid state, but when they are melted on or when they are dissolved in water, the ions become free. The ions become free from each other, and that's why they conduct electricity due to mobility of ions. Remember this. Thus, ionic compounds are good conductors of electricity in the molten or dissolved state. Okay, now they are showing one activity over here. In this activity, we have to show that ionic compounds conduct electricity in aqueous solution. So what we do is we take sodium chloride and dissolve it in water placed in a beaker. Now we place two electrodes in the solution as shown. Then we connect these electrodes to a battery, a bulb, a switch with the help of connecting wires. When you press the key, if the bulb glows, it means that the current is flowing in the circuit. On the other hand, if the bulb does not glow, that means the current is not flowing in the circuit. So we have to just press the key and observe that the bulb is glowing or not. So we do this experiment with different electrolytes, that is aqueous solutions, which are placed in this electrolytic cell. So aqueous solution of sodium chloride conducts electricity. Similarly, it can be observed that aqueous solution of other ionic compounds such as magnesium chloride, barium chloride, calcium carbonate, potassium iodide, copper sulfate, they all conduct electricity. And this shows that these ionic compounds are made up of ions. It is very interesting to note that, okay, this is something different. Okay, one more question I want to ask, that what if we take some molecular compounds, or you can say covalent compounds, in this uh, container? Will they conduct electricity? Molecular compounds like, let's say, alcohol or glucose solution or benzene or ether, will they conduct electricity? Carbon tetrachloride? No, they will not conduct electricity, and that shows that they are made up of molecules, not ions. Okay, so some extra information for you over here. It is very interesting to note that some metals and their salts impart characteristic colors to the flame. So take a small amount of sodium chloride on a metal spatula and bring it into the bluish flame of Bunsen burner. We will see that it imparts golden yellow color to the flame. Similarly, potassium imparts a violet color, lithium imparts crimson red color, uh, barium imparts grassy green color, calcium imparts brick red color, and so on. These metals are sometimes identified by their characteristic flame colors as well. Just remember this, some extra information. Okay, so after this, there are some solved examples which we are going to do in the live class. And the next part is occurrence of metal, which we will do in the next video. Okay, so for this video, you just need to take some notes. And in the next video, we'll finish the chapter, most probably, occurrence of metals, that is metallurgy. So see you in the next video. Bye-bye.